reflection of light, or light rays. So one of the things we notice about light is when you walk by a mirror, or even a shiny surface, the back of a, let's say a lake, or a nice, or the back of a spoon, right? Anything that's shiny, you can sort of see yourself in there. There's what we call an image of you. And it's actually weird, because if you think about it, it's like inside the mirror, there's a whole sort of little universe or a little world in there that we can never actually get to, but we seem to see it, right? What's going on inside the mirror. And we're going to try to understand all that by looking at how light reflects. Now, of course, we have mirrors that are flat, and we have mirrors that are curvy, like the spoon. And so we're first going to start with just talking about flat mirrors, so that we can get an idea of what happens there, and then we'll look at what happens when mirrors are curvy, like spoons. They can do all kinds of cool things. So first of all, let's just imagine, okay, a flat surface here, right? So this is a piece of something shiny, or anything. It doesn't even have to be shiny. I mean, it can be, we're going to talk about what makes things shiny and what doesn't. But let's just generally speak about a ray of light. So I'll use a ray of light here. I'll just draw a ray. I'm going to try to draw this. You should probably use a ruler to make it nice and straight, but I'll just do the best I can. I'm going to draw it in here like this. It's going to bounce. It's going to hit. Right. Actually, I won't draw. Hang on. I won't draw an arrowhead just yet. I'll put the arrow head back here, just so it's out of the way. So that's how we do it. If you put the arrow right on the top, it confuses the picture. So that's a ray of light that's bouncing towards this tabletop, or whatever this is, some object. And now what we've learned is that the light, or what we notice, is that the light's going to bounce off the object, but it's going to bounce in a very special way, right? So what we like to do is we like to measure sort of the angle that it's bouncing at. So what we do is we take a line that goes straight up from this spot where the light is striking. And then you'll notice there's an angle here, right here. There's an angle. When we do mathematics, we always use the Greek letter theta, which is a zero with a line through it like that. It's called theta. I'll put that over here just so you remember. And that's often what we use to describe angles in math and science. So you may as well get used to that. It's just a Greek letter. It's like calling it X or Y or A or B, right? It's just we like to use Greek. So that's the letter theta. And it's the Greek letter th. Makes a th sound. So that just means that that angle is some number. But here's what's interesting. Just like when you throw a ball against a wall, when it bounces off, it always bounces in the same exact way, doesn't it? It has to, because if it didn't, if it bounced weird or different each time, we could never play squash or racquetball or any kind of game where we had to judge, or play pool, for instance. How would you take a pool shot if it was just going to be a random bounce every time? You wouldn't know how to bounce the ball. But we can predict where the ball is going to go. We know that if it bounces in on an angle like this, it's going to bounce out on the same angle. So now I'm going to draw this line going out, but I'm going to try to draw it on the same angle like this. There's the outward going bounce. And what we should notice is that this angle is also the same as the other angle. So I can call it theta. Those two angles are equal. So I'm going to call this one theta with a little I, and this one theta with a little capital R. Okay? And so theta I is going to be the angle that the incoming light makes. So that's called the incident angle. Incident means incoming. That's the angle the light comes in at. And then the little theta R is the angle that it's reflected out at. So that's the reflected angle. And there's a rule that the angle of the incident angle is always equal to the reflected angle. That's the rule when you're bouncing things with light. It's also the rule when you bounce things with balls. It's the same idea. So then on this picture, what I'll do also is I will label this ray. This is the incident ray of light, the incoming ray of light, and this is the reflected ray of light going off this way. Okay? That little dotted line I drew, it's not really there. It's just a reference line that we use to measure the. You might ask, why don't we measure the angle down here between the ground or the object and the light? Well, the reason for that is that sometimes the surface can be bent or twisted or whatever, and these angles will not always be the same. But it's more effective for us to measure against this dotted line. Now, the dotted line has a name. He's perpendicular to the surface, right? He's straight up and down. It's a 90-degree angle right here between this line and there, 90 degrees. So we call this guy the normal, because normal is an old word that we often don't see much anymore, but it just means perpendicular. Okay? Perpendicular. That's what normal means. So we call it the normal reference line. We always measure our angles with light using a normal line that is 90 degrees to the surface that we're striking. And then, of course, this little spot right here where everything is hitting, we call this the incident point, or the point of incidence. Just some names, right? So incident point or point of incidence. We can also say incident angle or angle of incidence. And we can say reflected angle, or we can say angle of reflection. It means the same idea or the same thing. So what that means is that we can make a prediction, right, about how the light will reflect. Okay, so remember also, we've learned about colors and reflecting and absorbing of light. The reflected ray of light might not be as bright as the incident ray of light, because this object we're bouncing off of may absorb some of the light. It also may not be the same color as the incident ray, because we've seen how some rays can be absorbed, some colors, and some colors reflected. But if there is any reflection at all, this is how it will go. This is the way the reflected light would go. Okay, so here's what we can do as a little exercise, just kind of to get this in our head. And it's really quite simple, but we're going to need this later when we talk about mirrors. So if I take a surface right here, and I shine light in here like this, and it hits this spot. So I put my arrow back here, but it doesn't get confusing. All right? And I want to know, which way does the reflected light go? Which way does it reflect? Okay, well, what I would have to do is I would have to draw my normal line straight up and down. Now, the way you can do that on a piece of paper and get it perfect is by using a protractor, right? You put your protractor, which is, all know what a protractor is. It's that little half circle thing in your pencil case, and it's got all the little marks all around here, 90 degrees, and you use it in math to measure your angles, right? A protractor. So you can rest the protractor so that the bottom of it is on the line, the surface, and then you can go up here to 90 degrees and make a little tick mark, and then you can draw a line straight up, right? Make a little tick there, and make a little tick there, 90 degrees, and you can join the two ticks and draw your line. So that's how you can get this normal line on a piece of paper if you have to draw it. Then what you can do is you can turn the protractor. So the first thing, to draw the normal, right? Let me go through that again, just to make sure you all understood what I mean, okay? In fact, let me erase the normal from this picture for a second. Well, okay, let's do it down here. We'll do We'll come back to this picture in a minute. Let's say we want to draw a normal. Okay, so here's what we have, and here's the line coming in. So what we do is we get our protractor. I'll draw the protractor in blue, and we put it on here like this so that the line is right in the middle. There's a little mark on the protractor, right? And then you go up here to 90 degrees, right? And you make a little tick right there at 90 degrees. And then when you take the protractor away, what you're left with on the paper is a little tick, where you made your tick for 90 degrees. And of course, you know that that's lined up with this bottom part where it joins. Then you take your ruler, and then you just draw your normal line in, joining those lines. So you can make a normal line by using the protractor, by resting it on the surface in this manner. Okay, now, once you have the normal line, how do we measure the angle? Because we have to measure the angle between here and here, right? That has to be what we find out, the incident angle, which way is the light coming in. So once we do that, we can measure that by taking the protractor, I'll draw the protractor in red now, and changing its orientation. We're going to put the protractor sideways like this on the paper, so that we can measure, right here, we go down these ticks, and we just read whatever's lined up on the line there. Make sure this part is right on the 0, right in the middle of the protractor, right? Right at there, right at that spot. And then you measure it. So let's say we measure this, and it came out to be, I don't know, that looks like it's about 50 degrees. Right? And you read this way. You start here, and you read up this way. The protractor is designed so you can read from both sides, depending on how you put it on the paper, right? Okay. But you don't read this way and go all the way around to there, right? You always read the smaller angle to get to where you're going. So we don't do that. So let's say we did that process. We drew this normal in, and we discovered that this angle was 50 degrees by measuring it with our protractor. So far, so good? Well, now all we have to do is measure another 50 degrees on the other side of the normal, because the rule is that the reflected angle has to be the same as the incident angle. So what we do in this case is, I'll draw another over here. What we do in this case, okay, we've already measured this and we know it's 50 degrees. Okay, so now we take our protractor and we flip it and we place it this way. Flip it over on the other side of the normal like that. Put that right in the middle. And then we count over here to 50. And we make a tick at 50 degrees on the paper. Right? Look at the protractor, make the tick 50 degrees. Then when you take the protractor away, you have a little tick right here that you made on your paper. Then you get your ruler, and you join the point of incidence right through your tick, and that will make the angle right in here exactly 50 degrees. So you've made sure that this is now a 50-degree angle. And now you know which way that the ray will reflect. So you can use your protractor as a way of measuring. Any questions about that? Everybody's good? You may have to watch that a couple of times if you forget the process, but it's pretty straightforward. So now that we know how to measure incident angles and reflected angles, let's see what happens with a mirror. Let's look at a mirror sideways. So what I'm going to do here is I'm going to draw a blue line down the middle. This will be my mirror. But I said blue, right? I thought I pressed blue. I'm still getting red. Why am I getting red? Blue. Straight line, I'll draw as straight as I can. I don't have a ruler, I'm just eyeballing it straight as I can. So this is the side view of a mirror. Okay? So whatever happens on the left side over here, this is the real world. And then on this side, this is sort of like mirror land. This is what's happening inside the mirror, or what you would see in the mirror, right? So you have to think about standing on this left-hand side and looking in the mirror this way. So we can't really see what's on the mirror because we're looking at it from the side edge. And now I'll take a green light and or green marker, and I'm just going to make a random figure. Now, the simplest figure to make is a little arrow. Now, unfortunately, we use arrows for the light rays. And so all the diagrams use an arrow for the object in the mirror, and it gets confusing. So because it's confusing, I'll make the arrow sort of a little bit different from the light rays. So what I'm going to do is I'm going to draw this little arrow randomly like this, about that long. And I'm going to make them thicker so we don't confuse them. This is just a thing. It could be a dog. It could be a cat. It could be an avocado. Okay, it could be anything. But the nice thing about an arrow is it has a nice, convenient top and bottom. That's why we use it. Okay, so let's think about what happens now. So light from the light bulb is going to hit the arrow. And it's going to bounce off the arrow in all different directions, isn't it? But some of the light that bounces is going to go towards the mirror. So we're going to imagine what would happen to a ray of light that bounced off of, so we're not going to draw the light before it bounced off of the arrow. We're just going to imagine that there must be a ray of light right here, somewhere, right at the tip of the arrow. Light hits it, okay? So the light came in and hit it, but I don't want to show that part. It's confusing. So we're just going to leave that part out. So the light came in and it hit the arrow. And then after it hit the tip of this arrow, it bounced in this very straight line that you should use a ruler to draw, right towards the mirror, like that. Well, let's see what happens. Of course, it has to bounce off the mirror. But we know how to find the way it bounces. So what we do is we put our protractor on there, and we make a normal like this, straight out. This time it's sideways, so the normal comes out perpendicular to the mirror because we've flipped everything on its side, right? Then we measure this angle right here using our protractor. And whatever we measure it to be, right, if it's 20, then it's 20. Let's say we measure that. It looks like it's about 20 degrees to me. So let's say that's about 20 degrees. So I'll put a little 20 degrees there. We measured it with our protractor. Well, then what we can do is we can put the protractor on the other side and make a little tick, right, at 20 degrees using the protractor. And then we can draw the way this line would have bounced off the mirror. Now, when you draw this, if you're drawing it, try to make these angles the same. But don't draw it like that, because that's not the same angle, right? Remember, this angle, that's why we have the protractor, so we can do it really well. But I'm just going to do it with my eye here. That's pretty close, right? This angle that I've made now, right here, is also 20 degrees. So those two must be the same. Okay, fair enough. But here's the weird thing. Out here in the real world, this is where your eyeball is. So your eyeball doesn't see the light that's going towards the mirror. It only sees the light that's bouncing back off the mirror. Our eyes only see the light that bounces off of things, right? We can't see light streaming towards things. So our eyeball is right here. Here's my little eye sign, right? There's my eyeball. Put some eyelashes on the front. So the eye is looking at this light bouncing off this way, and the eye can tell which way the light is going. And because light usually travels in a very straight line, right? Our brains think so anyway. It turns out that light can bend and it can do weird things. But our brains have evolved to understand that light will be coming from a straight line. In other words, our brains don't know that there's a mirror there. They don't understand the bounce. So what they think is that this little ray of light came not just from the mirror, but it must have come from someplace way back over here. So we can take our ruler and draw this line all the way back, like that, nice and straight. This is where the line of the ray of light appears to have come from, because the eye does not understand that there was a mirror in the way. It just thinks there's nothing in the way, and the light just came straight from that direction. Okay. Now let's take another ray of light and draw it from the tip of the arrow to someplace else. Let's say now there's another ray of light, which I'll draw in a different color. I'll draw it in purple so that it stands out. This ray of light, it comes in like this, it hits like this, right? But we're not going to show that. It hits the tip, and it goes like this, and it shoots down towards the mirror, and it hits the mirror over here. So there's another incident ray that bounced off the tip of the arrow. Well, let's do our little game. Let's draw a normal line with our protractor, measure 90 degrees from the blue line and make this normal. Then let's measure the angle right in here. Let's measure this. This is a little bit narrower. I'm going to call that 15 degrees. I don't know what it is, but if you measure, you get it right. Then let's use our protractor to measure another angle on the other side that's exactly 15 degrees. And it comes out like this. Oops, see, now my angle's not right, isn't it? I can tell right away this is too big. So let me go back and try to get that even better. That's a little bit better. I think it's still too big. Let's try again. Now you won't have to guess like this because you'll be able to use your protractor and ruler and get it perfect every time. I'm just guessing on the board. That looks pretty close, right? Okay. Now, your eye, okay, it's the same eye, of course, on this side of the mirror, but I'll just draw the eye again. This eye would see the light over here, and the eye would think that this light, some eyelashes, it would think that this light came in a straight line from somewhere all the way over here. Like that. Okay? Actually, my line's not very good. Let me just go back and try to see. My line isn't super straight, is it? So it should be more like this, I think. There, that's closer to the truth. Notice something though. Notice that the two lines cross right here. Now what's cool is, I don't want you to draw any more lines on your picture because it's going to confuse everything. But I could draw 100 lines of light that bounced off the tip of this arrow in different ways. And watch what would happen. I'll do them fast. This one would bounce down here. It would bounce off at the same angle, and it would look like it came from there. One that went this way would bounce up at the top, and it would bounce off at the same angle. Whoops, that's not the same angle. It would bounce off here and bounce off high like that. But it would look like it came from there. And look at this. One that went straight in like this would bounce straight back, and the eye would think it looked like it came from there. No matter where I draw my line, if we follow the rules, they're all going to bounce in such a way that the eye thinks they all came through here. Isn't that interesting? And so that means the brain will think that there must be something there at that spot that is bouncing light towards the eye. And of course, it's going to look exactly like the tip of the arrow because that's where the light came from in the first place. And so what I can do is I realize that no matter what, it doesn't matter which lines I pick, right? It doesn't matter which ones I pick. They're all going to appear as if they came from this spot right here, which means that there's something special going on at that spot. And what's going on there is that is the spot where the tip of the arrow would be. Now be careful when you draw this. I'm going to draw the tip of the arrow sort of on a bent angle. Right? Now, if I play the same game with the bottom of the arrow, I'm not going to draw it again. I'll show you, but you don't have to draw it. Let's say I did the bottom of the arrow. Boom, boom. Well, this would go back somewhere there. I did it this way. Shoom, shoom. And it would go through there. Wait a minute. This would go like that. And then this other one, I could do it here. And then it would go up like that. And it would appear to come sort of through there. And then I could go here. And I could go, I could go here and back. And it would appear to come through there. And what we would find is there'd be another spot that all these arrows, all these rays from, oh shoot, I see what I did wrong there. Let me do that again. I got carried away. Going from the bottom. Let's go up here, like that. There, that makes more sense. And then let's do one here, like that, and then back, and it would come through there. Do one down here, like that, and it would appear. And there's a spot right here where everything seems to be coming from the bottom of the arrow. It's the same thing that we did on the top. But we don't need to do 100 arrows like that. What we'll find is that there will be a spot right about here that corresponds to the bottom of the arrow, and all the spots in between will follow the same rule. And the arrow will appear like that. So when you look in the mirror from this left side, you would see that arrow in there, sort of pointing away, right? In the opposite way. Because if I stand beside the first arrow on the left, it's pointing sort of over my shoulder. So inside there, it's a reflection. It would be pointing over my shoulder. Now you'll notice a couple of things on my picture. Because I didn't use a ruler and a protractor, I want you to look at some of these spots. When you draw this with your protractor, so you see this whole little spot in here? If you did it perfect, this triangle over here would look exactly the same. Mine looks a little smaller. And everything should be perfectly symmetrical on both sides of the ruler, or the mirror, sorry. So mine is not, because I'm just showing you with my finger on the board here. But if you can do this with a ruler in your paper, these two triangles will be exactly the same. And everything will be totally symmetrical. So this is called finding an image in a flat mirror. Okay? So I'm going to put that underneath here just so you remember that. Pen. What we're doing here is finding an image in a flat mirror. Another word for a flat mirror is a plane mirror, because it's like, remember how in math a plane is like a sheet of paper? Well, a mirror is like a plane. It's a planar surface, so we call it a plane mirror. Flat plane mirror. And that's the process. So just like I drew those two rays that reflect and follow the rule, I notice I didn't label my angle down here, but we would have had to measure this to be 15 degrees as well, right? So this is called the object, because it's the thing in the real world that's reflecting in the mirror. And over here we call this the image, because it's the thing that's in the mirror, right? Now remember, this is sort of an illusion. You can't see, you can't go around behind the mirror and grab the image. It's not really there. It's an illusion. And the illusion is created by the fact that the eye and the brain, they can't see the mirror. They don't know there's something in between there that's actually bouncing the light. And so the eye can only assume that the light that it's reflecting, or that it's hitting it right here, is coming from somewhere behind the mirror. And the same thing here. The eye can only assume that this light must have come from somewhere behind the mirror. Notice behind the mirror I draw dotted lines instead of solid lines. And that's to show that those are not real lines. They're just sort of guides to show us where it's coming from. There's no light shining behind the mirror. So that's why I'm drawing dotted lines on this side, because these are what we call virtual lines. They're not in the real world, right? They don't really exist. Virtual lines. Okay, so that's how you do this plane mirror sort of thing. And you find the image by picking any lines. It doesn't matter. I could have started with a ray going this way and bouncing that way. I could have done one that bounced down. Any two that you want. And you draw them with their normals and measure them properly, extend them backwards, and see where they meet. And that's where the tip of your arrow would be. Then what you do is you go to the bottom and do the same process. So you draw two rays from the bottom, anywhere on the mirror. Follow the rules, extend them back, and you should get a point that crosses right about there. And once you've done that, you can just fill in the middle. You can just draw in the arrow because you know the top and the bottom. So it's pretty straightforward. And that's the end of that.